Let's start. Please take your seats. This is the most exciting talk ever, the State of the Union of TCP, never done before, from a speaker you've never heard from before, Eric Dumazet.
Exactly. Thank you. Actually, because you don't know me, I did one slide after seeing this presentation yesterday. To give some bit of background, I started in with C Unix in like 40 years ago exactly. Yeah, that's. And at first, I had no access to the source code. So because I was so interested into this system, I had to disassemble it and do reverse engineering. That's, yeah. I think that why I'm able to debug in 5 minutes, just looking at the stack trace on the sysbot report, you know. Next thing I'm going to do is to answer Jamal's question this morning. You had an issue when you enable GRO, hardware GRO, and you saw a bigger memory utilization on the bus. The thing is, when you enable hardware GRO, you allow the NIC to send NIC in the frame faster to the receiver. And so if the receiver is not able to cope with the memory copy fast enough, then the queue on the receive socket builds up, it grows, and when you go above a given threshold, the CPU cache are completely defeated, meaning that you have more memory bandwidth just to evict the cache line from the NIC side and then repopulate the cache line a bit later, like 1 millisecond later. That might be the reason. So if you want to improve your results, you should reduce the TCP RMM. So you put like 500 megabytes, which is like 3 order of magnitudes too big. So you should put like 4 megabytes, and that should be fine. My bet on that. So I'm going to present this stuff today. So let's try to start right now. Overall health status of TCP. So yeah, today I'm not going to talk about ML, AI. It's not because I don't care. It's just because that TCP has its own life, you know, doesn't need ML to be successful. So, so we had like 370 patch just for TCP this year. MPTCP 200 patch. So MPTCP is not TCP per se, but it has some, you know, some interaction with TCP, of course. So I name here a list of contributors, but if your name is not here, don't be sad. It's okay. Right. To answer some question about efficiency of TCP whatsoever, I think right now we don't have to do magic things to reach line rate on a single flow. I do that every day. It's very easy. With TSO and hardware GRO, you can saturate line rate even on 200 gigabit NIC with a single TCP flow with arbitrary MSS, because MSS doesn't really, the NIC doesn't care if you are using offloads on the NIC, the MSS value, okay. And if you want to use zero copy on the receive side, then yes, the MSS value is very important. Because why? With the hardware GRO and the TSO, even at line rate, you need to cope with something like less than 400,000 packets per second, logical packets, and that's fine. I mean, you have a 3 microseconds per packet, perfectly fine. And that number includes the additional overhead for some NIC who would do the header split on the receive side, because some NIC implementation of header split is not optimal, meaning that the way they put the header is adding extra cost because you have 2 DMX instead of 1 per frame. So what happened last year? First thing, TCP AO has been added in Linux 6.7 finally after, I don't know, I don't remember, maybe 18 rounds of the patch set. Who is using today TCP MD5 or TCP AO? That's a question for the audience. Raise your hand. So I don't know why we put this stuff in the kernel in the first place. BGP, yes, it's nice, but why? Why do we have a specific handling in the kernel for that? I never understood. Yeah, we have other ways of doing crypto and, you know, authentication outside of the kernel. So yeah, okay, be it. And then last year we did a good work with Coco, Wei, some help from Daniel Borkman to make the data structure in the kernel more efficient, meaning that instead of not caring of the placement of each field on the TCP socket, INET socket, or all the networking net device fields, we try to study exactly which field was used in the transmit fast path, which fields were used in the receive fast path, and which fields were used in both paths. And so basically we reorder the field on this structure to make more efficient the stack for the case where you receive one packet every 10 milliseconds per flow. It's not going to help the synthetic benchmark when you use a TCP-RR or TCP stream, because what you see in this benchmark, you are sending so much packet per flow that the CPU cache are hot all the time, right? So that's optimization. It's hard to measure, but it really helps in our case to, when we are dealing like hundreds of thousands of sockets with very little traffic per socket, like health check, something like that. Next thing we upstreamed last year was the support for microsecond timestamp in a TCP timestamp option. That was something I did 10 years ago at Google. Initial idea was from Van Jacobson. At that time, he was really studying TCP dump all the time, and he wanted to have better resolution on the timestamp to get more entropy from, you know, the RTT values and stuff like that. So he wanted to know exactly how many microseconds we waited before one packet and the other, and that was the way we dealt with that. So it's upstream. By default, it's not enabled because nobody cares. I mean, but Google, I guess. So that was upstream last year. Another thing we did recently was, so there is a bit of ML here, right? On the second line, you can see TCP direct ML workloads on ARM cores. The issue we had when testing high throughput flow on ARM cores were that when you have the conflict between the bottom half handler feeding packets, new packets from the NIC interrupt, and the user space trying to consume this packet, very often the bottom half handler finds the socket being owned by the user, the application, and basically there's nothing the bottom half handler can do at that moment. It has to queue the packet into the so-called backlog queue, and this backlog queue is going to be processed by the user space whenever the socket is released. So, there's this, and when that happens, if you have like 10 packets in the backlog queue, the user space at the end of the receive message is going to send like 1 ACK per packet in the queue, if it's a 0 packet, right? And so the optimization I did was very simple. I detect this case, and I basically say, the sender doesn't care how many ACKs he will receive. The only thing he cares is the last one, right? Because ACKs are cumulative. Unless you have like SAC block, you don't care if you are going to receive 10 ACKs or a single one. You could care if the sender is CWIN limited, but if it's CWIN limited, there is little chance, very little chance that it's going to be overflowing the backlog queue. So some numbers, pretty interesting number. We got like something like 20% improvement by a single patch. That was pretty impressive. To continue on that, maybe we can work to generalize this idea of trying to suppress the hack. There is an outgoing discussion in IETF to have this hack request option to be negotiated between the SYN and the SYN-ACK. I'm not sure we need an option for that. I did something similar for the hack suppression some years ago. And so, for example, on a Wi-Fi network where the medium is half duplex, it's critical to not send hack, like too many hacks, because whenever you send hack, it prevents the other side to send you packets, right? And so actually, you get better results on Wi-Fi if you have some packet losses, and if the sender is using BBR, because BBR doesn't care about packet losses that much compared to cubic. And so if you make some experiments, Wi-Fi get much better throughput because of this hack compression. So we could just extend the idea to normal hack and get the same benefit, especially for Wi-Fi. So I forgot to say, I would prefer this presentation to be interactive. So just interrupt me, ask me a question. Yeah.
So I'll just comment on this. I know that many ISPs do very asymmetric rate limits. For example, you can have a gigabit of download and 20 megabits of upload as your internet connection. And as far as I can tell, the only reason you get those 20 megabits is you need 20 megabits of TCP ACKs in order to get a gigabit of download.
Yep.
So if you optimize this further, we'll end up with connections which are 1 gigabit down and 1 megabit up. So it's a little bit counterproductive.
Yes and no, because there is still Quick, right? So I'm not sure Quick does the same optimization. Or maybe they do already, I don't know. Sorry? Yeah, I think so. Yeah. So
the comment.
No, so Quick has the same stuff. So the stack compression was using the RTT as a base measure and a percentage of the RTT. So I was very conservative to use 5% of the perceived RTT. I think we could probably increase this 5% to something bigger.
I guess I should really comment on the Wi-Fi. There are people now who are asking us to do like ACK compression in the Wi-Fi drivers. It's really, really messy. I don't want to go there, so I think we'll need to explore some of this from our side in the future because we're reaching to, I don't know, a couple of gigabits, and the ACK flowing back is starting to have an impact on like, I don't know, 15, 20% of the bandwidth that you can get.
Yeah. So back to the Wi-Fi, I think you implemented the gyro part on the Intel driver, right?
So we have a GRO path. No, well, yeah, kind of. It's just a NAPI.
Yeah.
For the receive side, for the transmit side, we're building AMSUs so that you can just bunch the frames together more efficiently over Wi-Fi. But for the receive side, it's pretty much just a NAPI full consolidation. We don't have a special consolidation in the driver or something like that right now. Sorry, Srijit.
To continue from there, which is, so I think there are three aspects, right? Are you CPU overloaded? Are you media overloaded, which is more true for a Wi-Fi than it is for separate receiver transmitter? And the third is, what's the pattern, right? Like to the point about telcos being asymmetric, these large now 1.6 terabit data center networks have an opposite problem, which is they actually want to get very quick acts and very fast acts so that they can react and respond quickly. So I think I really am scared of whatever this IDF thing is going to show up with. But I think sender-driven adaptation is probably the best thing you can do. And RTT is probably one of the best tricks or one of the best signals for what it is that you need to get your ACK rate up to. Because if you're losing RTT, then you probably want to suppress anyway.
Yep.
So is that something you've looked at all?
Sort of. So that's a future work, right? So it's not even started yet. So, but yeah.
Right. If you're wanting comments in line, I was making notes in the back to tell you later. So about TCP AO, it is standard. People do run BGP on Linux, And so since Linux is about choices, you know, of course, it should be implemented and supported in the kernel.
Okay. Yeah.
Second, you mentioned about 200 gig now. So you have insights or beliefs about what 400 gig is going to be able to be 400 gig next can achieve for a single flow. When you start losing the MTU tricks and hitting other limits, do you think 400 gig is going to be realistic for a single flow?
I would think that if you have a 400 gig NIC, probably your bandwidth, memory bandwidth will be the same, or otherwise it's useless, right? Whatever protocol or transport you are using, if the memory bandwidth is smaller than the NIC bandwidth, there's nothing you can do.
Well, with GPU Direct, for example,
yeah,
right? You're not sending everything through, you're also going to the device.
Yeah, so for example, the GPU the direct thing is interesting because with SmartNIC, you can absolutely offload the protocol on the SmartNIC, right? So you can scale. So each NIC is going to do 200 gig or 400 in the near future. And so this NIC needs this throughput for the GPU, so the payload part, right? I think it should be fine.
Yeah, I think it's going to be doable as well. I was just trying to get your insights based on your testing.
So I'm not sure we are going to use TCP forever because there are other transports which might be better. For data center, I mean, in the rack, TCP has a lot of compatibility, legacy stuff that you don't really need. So maybe, I don't know.
Eric, just one comment. So I'm actually working for a satellite company, and ad compression is really needed for satellite communication, whether it's LEO or GEO or any even 4G, 5G, because thing is return link capacity allocation has to be based on something, right? I mean, they need to actually understand what is the incoming rate and then allocate the resource, right? And ag is, for example, in a slow start, right? If ag is blasting, then that actually creates a lot of queue overflow on the return link, and that actually increases RTT, and then all RTT based mechanisms are very much confused and then out. So.
Yeah, that's probably why you guys are using some proxy, something like that to do the stuff after the fact.
Now the word is going over TLS, so we can't really do that. So we try to actually expose all of the things to the word so we can get the help.
Okay, thank you. Oh, that's one.
You missed an opportunity with TCP/AO. The TCP/AO standard requires you to not implement MD5 unless you also implement AO. So it was a perfect opportunity to delete MD5 from the kernel, quoting the RFC.
Maybe in 5 or 10 years. Yeah.
So Eric, since the subject says ARC suppression, and you answered one of my questions, and no good deed goes unpunished. Do you have any idea why hardware GRO is giving us less ARCs than?
Yes, of course. So that's exactly what's happening. When the receive queue becomes full, then the kernel TCP stack no longer sends ARCs. It tries really literally to slow down the sender. So the number of ARCs naturally decrease. So when you reach, I think it's 66% of the receive queue capacity, we start to delay the ARCs. So that's a delayed ARC. Or when the user space does the receive message and drains the queue, then it sends the ARC at this moment.
Okay.
So there's some kind of feedback loop here.
That makes sense.
So that's why you saw less ARCs. But I mean, this should have been done already with dispatch. I'm not sure which version you were using. Well, it should be included in 6.5. Okay. And so another idea that has been floating around for quite a while, for this workload where user space and bottom half handler constantly try to acquire the socket lock, there's some kind of contention, but most of all, it's the backlog processing, which is a problem for user space because the backlog adds latency for whenever the user space has finished the work on the socket. So one idea was to, from bottom half handler, one expensive part in the stack is actually signaling. So sending the EPOL in or EPOL out if it's a EPOL application or any kind of process scheduler wake up, right? That part is very expensive. And we could very easily move this part after the socket lock has been released. That's something, this idea I've been floating around for years, but I never got the time to do it. In a similar way, in receive message, so when this problem with the queue being full starts to happen, user space is going to send the ACK, right, to signal, oh, there is more space for you, the sender, so you can restart the send. This ACK generation is very expensive because we have basically to traverse the whole stack, right? The IP layer, QDisk, and eventually the device. So that's very expensive. So we could do that after we release the socket lock, so that if you receive an incoming packet while you are doing this crazy expensive stuff, then the bottom half handler can just queue the packet just fine without the backlog cost. Is that clear for any question about that? No? Oh, so that's the stories about bugs in TCP. I heard this morning TCP was stable since years. It is, but we still have some bugs. Yeah, so this one was fixed last week actually. That was an interesting one. So basically, TCP user timeout is an option that the application can set to have a lower timeout than the RFC ones. The RFC ones are 2 minutes basically. And most applications don't want to wait 2 minutes, because if you wait 2 minutes, then you have a lot of sockets floating around in the kernel, consuming space, a lot of space if you are dealing with millions of sockets, right? Because each socket is at least 2 kilobytes, so that's a lot of memory. So this application wants to be like, wake up if there was no traffic for 20 seconds. Let's say you send something and then the retransmit tries, and nothing happens. So some applications decide to use 20 seconds. The bug was that if the timeout was expired, but the other side has sent us a win0 acknowledgement, then there was this bug where we were sending the packet every millisecond per socket. So that was a huge one. We also, so Neil Cardwell also fixed some interesting bugs where basically we had an issue with a field, the TCP return stamp, which was not properly cleared at the end of the loss event, meaning that the next loss event would eventually trigger some strange bug, because if you were looking at the TCP dump, everything was looking fine, but user space were getting a timeout, like a connection abort, right in the middle of the flow, of good-looking flow apparently. And this kind of bug was, wow, that was a very interesting one, because we discovered that in the cloud. You know, some customers had the migration of VM between one host to the other. And so while you do the VM migration, you have maybe 100 millisecond black hole in terms of networking. And after this black hole, we had like TCP flow being disconnected. That was very strange. So yeah, TCP is stable, but we still have some bugs to fix, and we find them all the time. I just want to mention something about busy polling, just to mention that our team is restarted the work on busy polling. For some reason, we ended our work on that in 2017. We thought that busy polling could not really be used in production, because at that time, the application was really doing the receive message or EPOL system call, and then eventually going to the device NAP EPOL. It's not scaling, right? If you want to have 100 application running on the host with 32 CPU, this solution cannot work. So the idea we had later was to kind of make the busy polling in the CAS thread, so in the kernel, and find a way to shift the amount of work we do from user space to the kernel. So for example, Wei Wang implementing something in the Google prod kernel where we're able to break the pipe in send message. So send message does just the copy, if there is a copy involved, or the page ref count for 0 copy. And then when the SKB has been added to the socket write queue, return to user space, meaning that the actual work of doing the TCP XMIT and ACK processing is done from a bottom half handler or like a car thread. So it's not done yet. We still have work to do. We are still doing the design of that, but I think that might be something useful even for application not using specifically busy polling, or trying to Joe D'Amato was trying to use all this fancy SO incoming, NAPI ID. You have to design your application very carefully depending on the number of queue you have on the NIC, something like that. While this kind of optimization could be generic and done in the kernel. The question of busy polling, I think it's a very nice topic, but my slide here is very small because still work in progress, right? So Kevin Young is planning to upstream the TCP Swift congestion control, the one that Nandita was referring to on the Falcon work Tuesday, I think. So the TCP Swift is the congestion control we use right now in the Google Fleet. It's specifically designed for network with round trip propagation time below 100 microseconds. And it's using hardware timestamping on the receive side and the transmit side. So obviously, it doesn't work for all kind of NICs because some NICs have very expensive clock acquisition. So for this kind of NIC, you can't do that, right? Because you need to timestamp like, I don't know, 40 million packets per second. So there is no way you can do that if the timestamp acquisition costs 1 microsecond, because you have to go to the firmware. During a prior Netddev conf, I explained that we're using an AMD host the no cache, the takes no cache copy option on the ETH tool. So basically, this is using move in TI instruction to, when we do the copy from user space to kernel, to not pollute the destination, the TCP cache for the destination data, because anyway, the NIC would pull the data at transmit side from the main memory anyway. So even if you put the data in the CPU cache, then you would have when the DMA access was occurring from the NIC, the CPU would have to flush its internal cache to the main memory and then main memory to the NIC. So that was adding some latency issue and cache pollution. So we tried to implement the same stuff for the receive side. The end result is that the experiment was not good enough, so we canceled it. But at least we conducted the full experiment.
So if I recall, on the no cache copy, we tested on x86 on no performance gain. Somebody told me on AMD there was a big performance gain. Did you consider different architectures maybe?
So it was not a gain on x86 Intel, because Intel had this DDIO stuff, right? So the cache, the level 3 cache, the last level cache is always used by the NIC with the DDIO. But on AMD, it's not the case. So that's why your option works beautifully on AMD CPU.
Yeah. Hi, I was just gonna comment. I posted an RFC like a couple years ago that allows you to use no cache copy when writing to kernel buffers. So it would allow you to basically pass it in a socket option into send message, so that you can decide as an application like when you want to use non-temporal writes. And I tested it on an AMD machine, and I saw like extremely significant performance gains. And I posted the RFC actually on the mailing list, and somebody replied think like incredulously, like, are you sure you're not running a debug kernel because your original numbers look really bad? So I think there's a lot of value in the non-temporal write path, and I hope to submit like an official patch set at some point to do this on like a per socket basis. Like I think doing it NIC wide has always confused me because, in my opinion, it seems like, and we can talk about this offline, but in my opinion, it seems that there are certain application architectures that have more or have stronger opinions about how they want to transmit data between different processes on the system. Is the easiest way for me to summarize it. But anyway, on the AMDs, I saw a significant performance improvement by using no cache copy and also by using non-temporal writes when writing to kernel buffers. So.
You know, thanks for confirming that. I always wondered. So that was the most disappointing thing when we implemented it and saw no performance improvement. Actually tried to take it out of the kernel, but Dave was kind of wise and said, no, let's keep it in. So good
yeah,
to know.
Please keep it in.
I think I should ask Google if we can grant you a spot bonus for this optimization, Tom, because you left Google before we could use it. Sorry. Okay, so the next idea I want to present today is the out-of-order early delivery. I think Tom mentioned that earlier today, but everything works fine if you don't have packet loss on the network, right? But if you have packet loss, what happens? What happens is that the receiver side has to store all the packet in the out-of-order queue, which is an arbitrary for each socket. And so whenever the hole is finally repaired after fast retransmit or RTO-based retransmit, and this out-of-order queue can be moved to the receive queue, right? And so what happens is that you have to store all these packets, so that's SKB, metadata, plus the page, which hold the payload, and that are accounted into the kernel, right? And so you have this sudden spike in memory usage. And so if you want to be able to absorb any kind of packet loss on the network, you have to provision for this extra memory. So in Linux, the default is to use 10% of the physical memory. That's a lot. Sometimes it's not good. It's not high enough, and so we start to drop packets because we exhausted the memory available for TCP. So the idea here is to extend the API to let the application get the packet before the hole can be repaired. That meaning not rely on the fact that receive message always deliver packet in sequence, but being able to get them in advance so that the buffers in the out-of-order queue can be reclaimed. So sometimes it can help, I think. That should also help the performance, the latency, because when you let like megabytes of buffer sitting in the receive queue or the out-of-order queue, when finally that can be transferred to the receive queue, the application receives an e-polling for potentially megabytes. And so it has to do either the copy or the zero copy with IUVEC, whatever scheme you use for zero copy. But that's expensive, right? Because if you have to copy megabytes instead of copying one packet at a time or two packets at a time when you receive smooth traffic, then you have this bubble and it takes time. So if you can, in advance, remove part of the bubble and let the application get the buffer sooner if they want to, that's a win. So the proposal is really to extend the API, and we need to take care of the standard receive message, which does the copy, but also the zero copy case. And the zero copy, you have two cases, right? The zero copy I implemented initially, plus the zero copy that I hearing can do, or TCP2X. So I'm not sure which API should be used. Either we can use a new receive message flag because we can propagate the information, the additional information in a control message, or new get socket option. I think it's always the same thing. If we extend new flag in the receive message, we make receive message slower for maybe a very corner case. Most people don't care about that. But most people won't use the new API, and so yeah, that's the choice we have to make. Any opinion on that?
Yeah, I have one quick question. So if that's the case, if you make the data with whole available to application and if they actually read it, like what about like when the retransmission comes, are you going to actually fill that hole in?
So the retransmit doesn't have to happen, right? It has been selectively acknowledged. We use SAC. So meaning when we receive this block out of order, we send to the sender, oh, okay, we received this part, but we are missing this part.
Oh, okay. So basically, you're changing the paradigm to,
No, it's not changing. It's already done this way. When you have a hole, basically you receive, let's say the sender sends 100 packets, and the first one is lost. The receiver is going to send multiple SAC, or eventually one if he's smart enough, telling the sender, oh, I've received 99 packets, but I'm missing the first one. The sender is going to retransmit only the first one. That's what we call the hole repair. So
yeah, but if the user have already read 99 packet, then
that's fine.
Then you don't really need to retransmit that one packet, right?
It can't. He never received the packet, so we can't say. So what's going to happen in this case? Let me explain. In this case, the API will provide the 99 packet, telling the receiver, oh, I'm giving you this 99 packet, but they are out of order. I'm telling you, I am missing, or then you are missing also the user space, this first block. It will be delivered later. Yeah.
Why not to have the out of order APIs in the IOU ring and not?
Can you repeat? Sorry, I missed the.
I was asking, why not have the new extensions in the IOU ring for out of order rather than in the receive?
Yeah, that's exactly that. We need that. We need this to extend IOU ring to support this new feature.
Second one is, when you do the zero copy with out of order, still need to maintain certain copies in the kernel for retransmitted packets to.
No, that's the sender which does that. The receiver doesn't have to hold anything. If the content of the packet have been put to user space, it's the responsibility of the user space to keep it, right? It's not.
But we want to avoid the copying it again from the kernel, or
it won't be copied again.
The same place.
It won't be copied. The whole proposal is to track which part has been put to user space, because we are going to remove it.
Yeah.
We are going to keep the SKB because we need to keep the arbitrary around, but the frags, the page frag attached to the SKB will be freed.
Yes, the memory is freed, but the metadata is still kept.
The metadata is still there because we need to understand which part was received or not.
What's the indication to say that now I can free the metadata?
The application has no power on that. That's really about the TCP stack. The TCP stack will know when the SKB can be freed. Basically, that's when we are going to transfer the arbitrary component to the linear list.
Yes, SKB metadata free understood, but the metadata of this is the out of order packets kept in the memory. When do we free it up?
So the arbitrary only contains packet we received, not the holes. The holes are missing in the arbitrary.
Your question about the received message, with this proposal, I don't see how this adds cost in the common code path. Just add a C message with the data in the case where the receiver is willing to get out of order data.
Can you repeat? I missed the.
Yeah, I don't see where is the cost in the common case coming from in the first proposal.
I think the cost is really the current code in receive message assumes the data is in a receive queue. But what happens if the receive queue is empty, but we have some stuff in the out of order queue? So we need to add a flag like here, and so we need to add a conditional testing a flag, and then look at the out of order queue if there is any SKB with frag. ready to be sent to user space.
Okay, that makes
So there's additional code here.
I guess to a certain extent, the static branch can solve these issues, but we found that even static branches are not free, unintuitively. I have another question. While data is in the retransmit queue, a duplicate can come in, even a partial duplicate, right?
Mm-hmm.
What is the behavior? I don't think it's specified in the protocol spec when the duplicates are different. Does it not matter?
So right now, whenever it happens, we just drop the second packet. We don't even
the first or the second.
We drop the second.
Okay, so this is the same behavior then.
There's this code about merging stuff, and so if you already receive payload, we just
okay, thanks.
There's a SNMP counter for that actually.
And they're like attacks based on having IDSs see different data because they drop the first and look at the second.
Yeah. So what could happen with malicious sender is that you could have an overlap. So in this case, we are going to keep the missing part, the part which was missing from the first packet. Yeah. It's a bit complex code.
So regarding the overhead, like if this configuration is like at the socket level, so and you basically move stuff from the reorder queue to receive queue, and it has all the sequence numbers, and based on that, the receive message, TCP underscore receive message, that can basically say, okay, this socket or this receive message call wants to receive stuff out of order. It can basically look at the receive queue and give it the out of order stuff. And when the new things come out of reorder queue, it can go into the
The thing is when the page flag are going to be removed from the SKB on the out of order queue, we'll still keep it, right? And so whenever we're going to transfer this SKB to the receive queue, we'll keep this information. So if some application mix a receive message with or new stuff with the flag or without the flag, there will be some marker on the SKB telling the application, oh, but this SKB is empty. So it has a sequence range, but you already consume that. So if you try to do something, try to read this, I will just send you some error code, something like that, to tell, oh, but you already got this sequence, or we could just remove it completely. Yeah.
I have another question about the transmit side. So basically, if you are doing out of order delivery to the application, and the after receive message is done, the receive window will be increased because the memory will be freed. So sender will now start sending new stuff, which will affect the back pressure. So how do we make sure that the ACK that is the data that is missing is retransmit?
No, you don't have to take care of that because we track on each socket the current memory, kernel memory we use for all the metadata. So if you remove stuff from this out of order queue, yes, the receive window will be increasing, but that's fine because that's exactly what we want. We want to be able to track the memory we use. And so the receive win is based on the memory we use. So if we use less memory, it's okay to increase the receive window.
I'm sorry, I'm talking about the how do we make sure that the transpender is actually giving more priority or like sends the missing whole first as compared
it has to. Otherwise, it's going to stall completely the transmit. Normally, a sender tries to send the lowest sequence first. Yeah, there's a rack algorithm try to do smart things, but ultimately the sender will try to send the lowest sequence first.
Okay.
And if it's malicious sender, it's going to freeze the flow. So.
One question is there a risk where if we are letting the user take these out of order data early, later on we'll come in with the actual data, is there a risk that we're just moving the bubble up to the user? Because imagine if there was you need that first packet to make forward progress on whatever your application is. What benefit would there be in such a scenario? If there's a bubble within the TCP layer versus there's a bubble at the user layer and they can not consume more until their user logic is.
That's true. I think you are referring maybe to zero copy on the receive side. Because
as an example, if it was like
yeah.
an encrypted file and like that first packet had like some important thing and the rest of the data does not make
Yeah.
sense to progress.
I don't think there is a generic answer. I think this mechanism will be used for some specific application dealing with long distance flow. I'm not sure. I don't think it's going to be used on the data center kind of traffic. It's more about long distance flow, 10 milliseconds, 100 milliseconds, where the BDP can be huge. Like we're talking of megabytes, like tens of megabytes per flow. So yeah.
So the out of order delivery functionality would actually be really useful for multipath TCP because we actually have the option, like that hole could be filled by another subflow.
Yes, but that would, I'm not sure because then.
Well, since we're in the kernel, we could tell it, hey, add that anyway.
It could be done, but then we need something from MTCP to tell TCP, oh, this hole has been repaired by some other flow, so it can zap the.
Right.
Yeah.
Right. So, but it does solve an interesting problem that, like, once you lose a packet on one subflow, have the head align problem.
Absolutely. Yeah. That's a good point. Oh my.
Hi. Is there any limit to the out of orderedness that you support? How much chaos can be thrown into?
Not really. Before, like 10 years ago, the out of order queue was a linear list, so it was hugely expensive to find the location for any insertion in the list. So eventually, we got rid of this linear list to an arbitrary, and so arbitrary is pretty efficient data structure. So yeah, you don't want to you don't want to have millions of buffers, but typically it's in order of thousands. Yeah, not more because of GRO, right? We store big packets in this out of order queue.
I think there's a lot of cases where the out of order packets could be decrypted and, for example, written to disk in any order because it just doesn't matter. You're just transferring a large file.
Yeah, or if you use PSP, then each frame is.
No more questions until he's done.
I'm almost done. That's the last slide. Another idea we had, I think that was 7 years ago, where I did this logic. That's going back to your setting of TCP RMM2 of 500 megabytes. What we want really is to have large RMM for long distance flow, right? And so we always can do BPF programming, right? Like ByteDance or others or Meta are doing. Like you can set whatever SK buff you want, SK receive buff. But if you want something generic in the kernel, something upstream, then it can be done this way. So way I did a threshold telling the base. So that's you see here the max, the cap of the receive buff limit. Instead of being TCP RMM2, which can be 16 megabytes or even more, we start at TCP RMM1. So at Google Data Center, we set this RMM1 to half a megabyte, meaning all TCP flow can have at least half a megabyte of buffers. But to get more, it depends on the RTT. And so if you put here a limit, let's say 1 millisecond, you have a slope depending on the RTT. So if the RTT is very small, you are close to the half megabyte mark. If the RTT starts to approach 1 millisecond or whatever value you put here, then it can be arbitrarily big, like in megabytes, 60 megabytes, 100 megabytes if you need so. So maybe some code because the code is nice. But that's very simple. Yeah. So the basic idea is just to compute the receive buff cap based on the slope, based on the RTT. So we use that, but we don't use that globally in the fleet. We use that only for the host with limited memory capacity for some reason, because maybe for other hosts we didn't care. I think that's generic enough improvement for general purpose. If you had that, Jamal, you wouldn't have this issue with your numbers, I think. Gary, if you are in the same rack, you don't need more than 1 megabyte of buffers. That's important because if you have too much buffers on the receiver side, then the page pool, page recycling optimization are defeated completely, meaning the NIC has to reallocate new page for each incoming packet. And it also defeats the CPU cache if you have a DDIO, stuff like that. So even for synthetic benchmark like OneFlow, TCP, it's nice to have. My last slide.
So I just wanted to ask you to be very careful with these changes, because on cellular networks and presumably on satellite networks as well, the RTT is widely varying, and it can start at like 8 or 9 milliseconds, and then it can be 60 or 70 milliseconds, fractions of a second later, and it can bounce between these, and it's very unpredictable.
Yeah, but I think for this kind of flow, you probably want the bigger buffers. If you have 9 millisecond RTT, then probably you want big buffers. That's more for data center-like communication, I think.
Do you have a plan to do for the other edge of the RTT? Because if RTT is super long, right, the buffer might not be enough to saturate the bandwidth, right?
Mm-hmm.
So the auto tuning of some sort would be very nice to have.
It's a hard problem, right? Because if you allow a single TCP socket to have more than, let's say, 60 megabytes, then it's going to break with 1,000 sockets. So, yeah, I don't think it's something that can be auto-tuned in the way you are. We can auto-tune things, but to a certain limit, and the limit is memory, right? So
I'm not really saying do this for all TCP connections, but like some of the TCP connections.
Yeah, it's interesting because I had this bug recently. Yeah, I forgot to mention that there was a change last year about trying to make the kernel memory occupation to receive window a bit smarter based on the occupation we have on the incoming packets. For example, if a NIC uses a 4K page for incoming packet, even if you receive a 1500 byte packet, then you have an overhead of 60. You use more memory than needed, right? And so there was a change like that. And somebody complained because their application was slower. And guess what? They were just using SO receive buff to 60 kilobytes. So, in 2024, we still have people thinking that letting application to choose the optimal size is better than letting the kernel do the auto-tuning. That's wow. How TCP can perform with 60 kilobytes of buffers, I don't know. It's like, I don't know. I have no idea how it can work. It's not even the size of one packet, 1 0 packet. So
I think on Android now, the default is around 16 megabytes on any high performance, i.e. like 1 gigabit network. I wonder if usually the number of sockets is very low, right? We're talking about dozens, not thousands. I wonder if you could do something like just simply know how many sockets there are in the system, and the first 100 could use 60 megabytes or 16 megabytes or whatever. And if you go above some threshold, then you just start doing less per socket.
Yeah, that could give a huge advantage to these 100 sockets, right? Because if they are long-living sockets, then...
Yeah, but in practice, you never have that many anyway, right? At least it could be configurable, obviously, but on mobile devices, you're lucky if you have transfer on a couple.
We better cut it here. So we could go on for a while. Thanks, Eric.
Thank you.
All right.